Good morning. So let me explain how this talk is going to work. It's mostly going to be quotations from smarter people. That by quoting smarter people, I'm going to try to make myself look smarter and perhaps try to convince you about the point of my talk. Okay, so but I should point out, I've never met any of those people. Most of them are dead. There's no evidence that they would agree with anything that I'm about to say. So just to make it clear what I'm about to do. So I'm going to start with the mathematician Bertrand Russell, who said, even when the experts all agree, they may well be mistaken. And a lot of crackpots and cranks really like this quote, because they think it says, if everyone in the world thinks I'm wrong, then Bertrand Russell says I might be right. And that's not what Russell's talking about. He's not talking about the cranks, he's talking about the experts. And why is it that when a new thing is discovered and the thing is proven true, most of the experts will still reject it? So why is that? And it has to do with the fact that the mathematicians are all human beings. And we think in terms of paradigm. We have a model of thought that through our entire lives, we're building a data structure in our brains where pieces of information or experience come in and we assemble them together, and that's what our intelligence is made of. And it's really remarkable the way we're able to do it, because we can take something that we learned over here and something over there and connect them. And that's how we discover things, and that's how we go forward. That is something the machines have not figured out how to do yet. And that's why we all still have jobs. But this way that we build this structure isn't perfect, and it suffers from a number of defects. One of them is the confirmation bias. So pieces of information which come in through our senses, which are compatible with our internal model, are easily accepted even if they are false. And pieces of experience which come in which are not compatible with our model will be rejected even if they are true. Carl Sagan, the astrophysicist, said, in science, it often happens that scientists say, you know, that's a really good argument, my position is mistaken. And then they would actually change their minds, and you would never hear that old view from them again. They really do it. It doesn't happen as often as it should, because scientists are human and change is sometimes painful, but it happens every day. I cannot recall the last time something like that happened in politics or religion. So I think the important sentence here is this one. It doesn't happen as often as it should, because scientists are human and change is sometimes painful. In fact, change is sometimes painful because it causes confusion. That we have a set of things that we have always believed, and then we find out that something fundamental about what we believe is not true. That causes us to question everything about what we are. And that can lead to fear. You know, if it turns out my fundamental assumptions are false, then I know nothing. And yeah, you know, that can be really scary. It can also cause embarrassment. You know, you might be someone who has been loudly proclaiming a particular point of view, and that turns out to be wrong. It's hard to suddenly step back and say, sorry folks, I was wrong about all this. Generally what they'll do instead is shout louder. You could experience financial loss. For example, you might be a consultant who is big in pushing a particular point of view, and suddenly that point of view is false. It means you're starting over with everybody else now. And so you've lost your competitive advantage. And so it can trigger the fight or flight response, where either you'll want to attack anybody who's representing the new point of view, or you want to just run away and try to avoid that argument. The economist John Kenneth Galbraith said, faced with the choice between changing one's mind and proving there is no need to do so, almost everyone gets busy on the proof. So it turns out all this stuff happens in programming, too. We think that we're the most logical people on the planet, but it turns out we're also human beings, sorry to say. So we are also subject to confirmation bias, and it affects the way we think about programming. Now, there have been a number of really important paradigms in the history of programming. One of the first ones was the stored program concept, which von Neumann and his colleagues at Princeton came up with. And that still dominates today. Now, it turns out that before that, there was something that we now call analog computing, where computing would be done with gears or voltages. And the people who were doing that style of computing didn't make the digital transition. The people who started with digital computers were mostly mathematicians and engineers who were coming into this who had never done any kind of computing before. And so when you're fresh and new, the new paradigm can be really easy. It's only if you have experience that the paradigm is hard. Almost immediately, we discovered a problem with the von Neumann concept, and that was that we needed subroutines. We needed some way of representing a piece of program which could be used multiple places in the same program or be reused in other programs. That was not anticipated by von Neumann, and it was discovered very early when the von Neumann machines started being programmed. And that was an easy transition to make because it was so obviously the right thing to do. So, and everybody was still very new at programming, so we had no trouble with that one. And most of our paradigms fall from that. For example, structured programming, the idea that we get rid of the goto. That was really controversial for many, many years. Today, we now recognize that the goto debate was silly, that all of the arguments against goto were false. But that didn't stop a lot of really smart people from advocating that we have to stay with the goto, even though it's good that we eliminated it. In fact, one of the major advocates for getting rid of it was one of your people, so good for you. The next step forward was methods, which leads to object-oriented programming. That was a really important step forward, and not a lot of people were prepared to take it, and so that led to C++ and other terrible things. One that we're going through right now, and JavaScript is at the forefront, is higher-order functions. These are functions that take functions as arguments and return functions as results. I think this is the most important idea we've come up with so far, and JavaScript is leading the way here, so that's really good. If you haven't gotten into higher-order functions yet, you really need to be doing that. There's growing interest now in pure functions. Pure functions model mathematical functions, where functions have no side effects, cause no mutation. And there are some really, really good properties of pure functions. And there are some advocates who are saying that from now on it should only be pure functions. And I don't think that's going to be the case. Now that might be, I think purity is important and we should strive for as much purity as we can, but I don't think we want to be 100% pure. I think we want to be closer to 99.44% pure. And the reason, well, it could be this is my own confirmation bias, that I'm not completely ready to move up to the purity paradigm. But I think my reservation is right, that it turns out the universe is not pure, that it's full of you, for example. It's full of humans, and humans are not mathematically predictable. And the lambda calculus doesn't explain how networks work. So I think we still need to have state somewhere. We just need to be smarter about how we manage it. So it turns out that progress waits not on discovery, but on consensus. That we like to think that something is discovered and, oh, we've been waiting for this to be discovered, and then suddenly we all follow. And that's not how it happens. In fact, it very rarely happens that way. Max Planck, the physicist, said, "A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die and a new generation grows up that is familiar with it." And this is why progress is slow. Now, from our perspective, it's pretty fast, but even for us, it's slow. You look at how long it took to get rid of goto. And we didn't get rid of goto by changing minds. We had to wait for a generation of programmers to retire or die before we could get rid of the goto. And it's true in physics, it's true in everything. Planck said it again much more cleverly: science advances one funeral at a time. So a paradigm shift is something that makes us defensive. And there are a number of responses that people might have. One is to shoot the messenger, that will attack anybody who's advocating the new perspective because it's threatening. Another is to become a champion of personal preference. All points of view are equally valid, even mine, which is provably false. That personal preference turns out to be an extremely poor criteria for deciding what is true. You hear lots of statements like this: I do not understand how X can be true. And I thinks that is proof that X is not true. But in fact, this says nothing about X. It only says something about I. It is proof that I is not qualified to say anything about X. But we hear arguments like this all the time. I've never used something like that, and I'm very successful doing what I'm doing, therefore that thing can't possibly be important. We'll also get violent disagreement with irrelevant details. They'll look for something that, and use that as the reason to reject everything else. They will intensify imperfections, and if they cannot find an imperfection, they will invent imperfections. They say, I hear you saying something which is obviously not what you said, and I disagree with that. And then we'll see partial adoption. Like object-oriented programming is going to become important, but we really don't understand what object-oriented programming is about. C++ makes a lot of sense. And we'll see obsession about performance, that we'll look for some case where the new paradigm does not perform as well as the old paradigm, even if that difference is irrelevant in most cases, and even if it isn't even true. We really like performance, and we will use performance to drive things which are ultimately really bad ideas, or to reject things which are really good ideas. Moore's law should have completely changed the way we think about performance. You still see people who are chasing after cycles. If I can shave a couple nanoseconds after this, it's going to add up, and it doesn't. Nanoseconds are really tiny. It takes a lot of them before they become observable. More computing sins are committed in the name of efficiency without necessarily achieving it than for any other single reason, including blind stupidity. This was William Wolfe, who's happily still alive. He's the only one I'm quoting who's still with us today. So something that we all enjoy is the new shiny object. But the new shiny object is always the old paradigm. If it were the new paradigm, it would be weird and confusing and easily misunderstood. So if a new feature comes out or a new package comes out and suddenly everybody gets really excited about it, it's pretty likely it's just a redressing of the old stuff. In fact, it is really difficult to distinguish a new paradigm from a really bad idea. We just can't tell the difference. So I'd like to share with you my thoughts on what the next paradigm is going to be in programming. So to review, the old paradigm is sequential programming, that we do computation by doing one thing after another, a list of instructions, boom, 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 we go through. Now, we've gotten very clever at finding interesting ways to compose that stuff, and by having nested functions and higher order functions, we can get very sophisticated in the way that we sequence things, but it is still one damn thing after another. And we've gone a really long way with that. But that's a style of programming which really is best applied to a single machine trying to solve a single problem. Everything else really doesn't fit in that model. So I think the next paradigm is going to be asynchronous message passing. I think that's the thing we should be looking for in our next set of systems and our next set of languages. So in asynchronous message passing, we're sending a message from one process or a system to another. And the sender does not wait for a response. The sender is free to do more work, including sending more messages, possibly to systems it's already sent messages to, or to other systems, or even itself. Every receiver has a queue or mailbox that holds the incoming messages, and the messages will be handled one at a time. And it's a shared nothing architecture. Now, up till this point, we've invested very heavily in shared everything architecture, mostly under the premise that it gives us the best performance. But we have reached the scaling limits on that. And the next step forward is going to be shared nothing, because then you can spread your stuff over an infinite number of machines, and ultimately that's the only way we're going to get better performance. Now, if this sounds familiar to you, you're probably right. For example, the actor model, which was discovered in 1973, is this. It's the idea that you've got computational entities which are unique, which share nothing, which send messages to each other. And the actor model is capable of performing computations that the lambda model cannot. So it's very powerful, and it also seems to fit the way that we're building our systems today. If you think it sounds like post message, you're right again. We first saw post message with Google Gears, and it's now in browsers, and it's a way that you can talk to workers, and it's a really good thing. And again, it is or should be a shared nothing model where you send a message and you don't wait necessarily for that message to be processed. The requester is allowed to continue processing immediately, and we'll get a callback or some return message sometime in the future. If this reminds you of Node.js, you're right. This is, in fact, exactly what Node.js is. It's an actor that implements JavaScript. So it's something that can sit in the network, that can receive messages, that can send messages to other things. So in many ways, we have already adopted the new paradigm, but not completely. There are a number of instances where we are still clinging to the old paradigm, and that makes it difficult because we're using tools which really are not adequate for doing what we need to be doing, and it also forces a mental mindset which is working against our interests. So examples of that are RPC, HTTP, SOAP, and REST. These are all things which are the old paradigm. They're trying to distribute the idea of having a subroutine call going over to another machine so that the requester machine stops and is locked, is frozen until the next thing resolves. And that's exactly the old paradigm. That's what we don't want anymore. Fortunately, we've gotten rid of SOAP, mostly. We're still stuck with REST. Eventually, we'll get away from that as well, I hope. In Node, we've got the sync functions, which are tragically terrible because the sync functions cause blocking. And when you use those functions, Node instantly changes from an extremely efficient system to an extremely inefficient system. Those functions shouldn't exist, but because they exist, there are idiot developers who think they have a right to use those stupid functions. There's a lot of interest now in async and await. The goal with those is to allow you to write asynchronous programs without understanding how asynchronicity works, that if you put these decorations in your code, then you can stay sequential and not understand what your code does, which it's like C++ again. This is the wrong direction. What we need to be doing is embracing asynchronicity. And asynchronicity and asynchronous message passing is a great paradigm because we've got a single mechanism which provides concurrency, which is the ability to do multiple things at once, communication, which is how we move information over the network, both command and data, and security, because we can control access from one machine to another. So this is the thing that we really need to be getting into. So I've prepared a couple of things to make it easier for you to do that. The SAFE protocol and a JavaScript package called Parsec. So I'll start with the SAFE project. SAFE rhymes with safe, in case you're not sure how it's pronounced. So SAFE is a secure, efficient, asynchronous JSON and blob messaging system. So it's all about sending JSON packages or packets to some place, or blobs if you have something which is not efficiently represented in JSON, and back again. It does not require DNS, HTTP, certificates, or passwords, because all of these things have been proven not to work. They do not give us secure, efficient systems. So SAFE kind of scratches everything away and goes back to TCP and builds on top of that. Safe can set up a secure connection and authenticate both parties in one round trip, which I think is as good as you could ever hope to make a protocol. So right now in HTTPS, we pay a huge time penalty, many round trips in order to get something started. And because of weaknesses in certificates and DNS, you might not even be connected to the party you think you're connected to. That's not the case with Safe. Safe also allows for 2 flavors of message sending, which allows a broader range of applications. We can have normal sends, which will have persistent retry, will make a best effort to try to make sure the message gets delivered, and a status send, which will make its best effort to try to send the most recent version of a message, which is something you might want to do in games or in telemetry, where if there's a network partition and then we're reconnected, you don't want to wait for everything which ever happened before you find out what's happening right now. And so it allows to do that. And both of these are asynchronous message sends, which means it just sends a message. It's not a request response. It might be that the way you use it is you send a request and you get back a response, and that's fine. But it's also much more capable. You can be doing push, you can do fan out, you can do lots of different patterns. It's an open source project. It's available on GitHub. Right now, it's only available for Node. We're hoping to eventually get it up on iOS and every place else, but we're not there yet. Because it is open source, if you'd like to help us get onto the other platforms, that would be great. So the universe, it turns out, is completely asynchronous, fully distributed, and highly parallel. And our programming model should embrace this truth and not try to reject this truth. So we need to be managing asynchronicity. And one of the ways we can do that is with nested callbacks, which has been proven to be a terrible way to do it. It's trying to do the sequential paradigm, and it just works extremely badly. We've made an effort at doing promises. Promises were invented at a company that I founded several years ago, and promises used to be great. Unfortunately, in transiting into JavaScript, they kind of got messed up, and most of the really good things about promises have been lost, and they've left an unnecessarily confusing programming model. And we've already talked about async await, which works and produces cleaner code, but it's the wrong paradigm. It's trying to keep you in the sequential mindset, and you'll never use the network correctly if you're using async await. So I came up with a library in JavaScript called Parsec. Parsec is a JavaScript library for managing asynchronicity in server applications. It comes with 5 functions: sequence, parallel, parallel object, race, and fallback. So let me show you these functions in more detail. Sequence takes an array of requester functions. A requester function is a function which, when you call it, will cause some service to be happening. And it will also take a callback, which it uses to deliver its result. So here I've got a sequence where I'm going to try to get the user data, and use that data to get the preference, and use that information to get the custom nav. So the sequence function will return a requester function, which, when we call it, will cause that sequence of things to happen. The parallel function will cause a lot of things to go into at the same time. It doesn't add parallelism to JavaScript. What it does is it allows JavaScript to take advantage of the parallelism of the universe. So it'll take an array of requesters and allow you to start them all at once. So this one will get stuff by getting the nav, getting the ads, getting the message of the day. It can do all of those at once because these requests are not dependent on each other. And that's the only way that we're going to get really high performance going forward. Because if you're not doing things in parallel, then the time it'll take is the time it takes to do each one. Whereas if you do them in parallel, you're only paying the time to do the slowest one. And if it's a lot of things, you can get significant performance improvements, factors of 10 or more, which are not something you're going to get by twiddling with your code. We can also deal with optional things. I want to get the nav and the ads and the message of the day. I also want to get the horoscope and the gossip, but those are low value, and I don't want to be delayed by those. So if I can get those before the main things finish, then fine. If not, or if they fail, we're good, we'll keep going. Then a race is similar. We'll start a bunch of things at once, and whichever one completes successfully first will win. So we've been getting bad performance from our ad network, so we'll tell our ad suppliers, every time we have a position to fill, we're going to ask you and 2 of your competitors, and whoever comes back first with a placement will get the slot. Then we can also deal with fallbacks, so we can try things one at a time until something succeeds. So in this one, we're going to get the weather. First, we're going to go to our local cache. If that fails, we'll go to the local DB. If that fails, we'll go to the remote DB. Parsec can also deal with cancellations. Any requester can optionally return a cancel function. And if we call the cancel function, it'll attempt to cancel the request. There's no guarantee that the cancellation will happen before the time completes, and cancellation is intended only to stop unnecessary work. So if we decide that this thing, we no longer are interested in it, we can just stop it. Parsec can also deal with throttling. Parsec can easily overwhelm some incompetently architected systems. For example, you might have 1,000 requesters, and you might want to throw them at something, and it falls over because it can't handle that many simultaneous requests. That should not be happening in the 21st century, but it still happens a lot, so Parsec can be throttled. Parallel and Race can start all of their things at once, but if we don't want to start them all at once, we can put a throttle on it, which means we'll only start as many as some limit, and we'll never have more than that number running. So this is the set of Parsec functions. It's a really small library. I think this does everything you need in terms of managing asynchronicity. And it's on GitHub, and it's free. So I think the next paradigm is asynchronous programming. And I'll finish by quoting the philosopher Schopenhauer. All truth passes through 3 stages. First, it is ridiculed. Second, it is violently opposed. Third, it is accepted as being self-evident. Thank you.